Hi, welcome back. So this is the third series in section 4.4, and today we're going to do the second fundamental theorem of calculus. Okay, just a quick reminder to go over what the first. Let's see if I can find this. The first fundamental theorem of calculus was. So here is really the first fundamental theorem of calculus. Okay, this really becomes second nature. Now all it's saying is that when you want to integrate a definite integral like this, you evaluate by finding the antiderivative of lowercase f and then plug in the values for a is called the lower limit and b is called the upper limit. Okay, so that's the first FTC. Today it's all about the second FTC. So really this chapter here, or this section 4.4, is pretty meaty. Okay, it's got a lot of concepts in there, and I hope that you guys are going to watch this couple of times because like I'm saying, that there's a lot of substance in the in this section. Okay, I don't have my mouse here, so things are going to be scrolling in a very old-fashioned way, unfortunately. Let me see if this thing works. So the second FTC, here we go. Okay, well, let's do a simple exercise. Okay, so let's do this integration using the FTC. So you know the antiderivative of cosine is sine x. Okay, and you can plug in x for upper limit and 0 for bottom limit. So then this guy becomes sine x minus sine 0, which is equal to sine x. Okay, all right, so notice that this is a function. Okay, and if I now differentiate that function and call it f prime, I get cosine x. Well, look what's happening. Nothing magical. Now this is really true only if the bottom limit is not only a 0 but some constant or some number, and the upper limit is a pure x, okay, not a function of x, not like x squared or square root of x or something like that. So showing you what the statement of the fundamental theorem of calculus, the second one. Okay, scrolling in a very primitive way here. I should have brought my mouse. So here is the definition of the second FTC. Okay, now pause here for a minute for you guys to absorb. What it's saying is that if you have a definite integral with x as an upper limit, okay, and a constant as a lower limit, and if you differentiate that, okay, so in other words, you are differentiating this quantity, and I had told you earlier that this quantity, because there's a variable x there, turns out to be a function. You can differentiate it, okay, and your result is no different from what the integrand is. Okay, so that's the second FTC. Let's do examples. Okay, so from here on out is all examples. So the concept is fairly simple. All the meat is in the examples. And so the first example I'm going to do is number 76 on page 293. Let me go bring my book up. Number 76, page 293. So here it is. Okay, here it is. I'm going to snip it. I wonder if I can make this bigger. It's really strange the way this window gets created. 176, so I'm just going to go like this and see what happens. Can I get a bigger? Oh, okay. Now I get a bigger chunk. So I'm doing this problem here. Okay. Now I'll do it two ways. Okay, I'll do it the old-fashioned way first to make sure that you understand what's going on. So notice it's asking you to integrate. So this is going to be equal to integral from 0 to x of t cubed plus t dt, which gives me t to the fourth over 4 plus t squared over t from 0 to x. And if I plug x in there, I get x to the fourth over 4 plus x squared over 2. And notice now that this is a function of x. Okay. And the second FTC is what happens if you differentiate this? Well, if I differentiate this, then I get 4 times x cubed over 4 plus 2 times x over 2. I can simplify, and I get x cubed plus x, which is equal to x times x squared plus 1. Well, look, okay, look at this. And look at the integrand. Same thing except that you actually put in x wherever you see t. Okay? So we could have done this problem straight out without doing all this work, just use the FTC. So the way you would do this is number 76. The way you would do this is that f prime of x is equal to x times x squared plus 1 by just taking the upper limit, which is the variable x, and putting it into whatever the variable of integration is in the integrand. Okay, so application of the FTC, the second FTC, is pretty trivial. Okay, there are obviously caveats, and I'm going to do some examples to show you what the caveats are. Okay, next one I think you are supposed to do, and since you are not here, I get to do it. And number 78. Okay, I guess I shouldn't have closed that other window, huh? Okay, number 78. Gonna go snip again. Snippety snip. Number 78, same kind of process. I want to find f prime of x. Okay. Notice that this is not a 0 this time, but this is a 4. Doesn't matter as long as it's a constant. Okay, and then the upper limit is just an x. I'm going to use straight out the second FTC, and all I need to do is take the x and plug it in for t. My answer is that. Okay, don't have to do the long process of actually doing the integration, substituting, and then differentiating. Okay, that's the beauty of the second FTC. It gives you the results very quickly. Okay, right, 4.4. So second example. Third example, I do yet more. Things I do for you guys. Things I do. Number 82. Okay. Again, there's nothing new in here. It seems a pretty straightforward problem. Nothing very tricky or anything. Okay. So number 82. Okay. And you're asked to find f prime of x. Okay. You have to find f prime of x. Notice that the upper limit is x. The bottom limit is a constant. Just put in x wherever you see t, and lo and behold, that's your answer. Okay, that's your answer. So, third example, pretty trivial. Number 84, you're supposed to do. You're not here. I do. Okay, so number 84, same kind of process. You're asked to find f of x. Notice again that the top number is x, the bottom is a constant. All you do is plug and chug x for t, and lo and behold, that's your answer. Next one up. Now comes some interesting. Okay, so curveballs. calculus is not calculus unless there are curveballs, period. Number 87, page 293. Number 87, page 293. So actually I'm going to do both 87 and 89. They're both curveballs. Okay. So the first thing to notice is the curveball is that the bottom limit is an x and the top limit is an x plus 2. In the FTC, if you remember, you can only have a constant here and x there. Okay. Or I'll just do FTP. Okay. That's all you're allowed. So we've got things that are a little different. Well, no big sweat. We're going to rewrite these things. Okay. So for number 87, okay, for number 87, I'm going to rewrite this. Now I'm going to rewrite it using certain properties of integrals. Okay. I can always break that integral up into x to some number 4t plus 1 dt plus from some number to x plus 2 of 4t plus 1 dt. So this is one of the properties that you've learned about integrals, probably maybe in 4.2, 4.3 maybe. What it's essentially saying is that, again, just to refresh quickly, what a definite integral is. Okay? So let's say you've got a function, okay, and remember an integral is just finding the area underneath the curve from A to B. And what I just did, using the property that I just did, is say that I can find this area that I want. Okay, let's just first read this. I want that area. Okay. I can find that area by doing this. I can break this up into two regions. And I can find this black shaded area first, okay, which would be an integral from A to C. And then I can find the red region, which is the integral from C to D. That's the property I'm using. Okay, that's the property I'm using. So going back to our problem here, okay, I have taken the original integral fx, broke it up into these two. Now there's still an issue here. Okay, notice that this is the lower limit. We needed x to be on the upper limit. Okay, that's what the FTC is about. Well, second rewrite. From properties earlier on, you should have realized that that integral can be written as minus a to x. When you interchange the limits, you stick a negative sign in front of the integral. And then the other one doesn't need to be changed much, except for I'll show you, well, how do I show you that? What am I going to do? Oh, perhaps I need to do an example first before I finish this off. Okay, I just have to create an example first before I do this. How am I going to do this? Can I go back and snip this guy? Can I snip that? Let's see if I do a new. Okay. Oh wow. Okay. Okay. Snip that. So I do need one example before we go on to that one here. Okay. And now I'll just create one for you. Okay. All right. So let's say we go back and do this. T dt from 0 to x squared. Okay. T dt from 0 to x squared. And I can't use the FTC right now because my FTC tells me that this is going to be x squared. So what I'm trying to do is create a result that's going to help us get the answer very quickly. Okay. So the old-fashioned way would have been, I'm going to integrate this, stick x squared in there. This gives me a new function. I differentiate that, and I get 4x cubed over 2, which is 2x cubed. Okay, so this is my final answer. Well, look what we could have done, okay? Supposing this had been an x, then I know that my f prime of x would have just been equal to x, right? I take the x and shove it in there. but it has